Hello everyone. Today we're going to be talking about H-NMR, which is hydrogen nuclear magnetic resonance. It's an instrument that's used to analyze the structure of molecules. This is going to be a two-parter because the software I'm using can only do 5 minutes. That's not enough time. All right, so what is the point of H-NMR? It allows for the quick identification of molecule, and it can be used to determine the structure of a molecule. And its main thing is that you need to know is that it tests for the environment of protons. That's the thing you need to know. Um, One, I've used these before. The main use of it was you do a reaction and you wanted to make sure you got the right product. So let's say I was oxidizing it. If I put it in an H-NMR, the oxidized product should read out differently than the unoxidized product. So if I get the right readout, then I know I have the right product. How does it work? You're basically the instrument. You put in a little tube in the instrument, and then a little magnet rotates around it, and this rotation creates a magnetic field, and the protons around your molecules can either align with that field or go against the field. And when they go against the field, that means that they're higher in energy. And when those higher in energy hydrogens, when they relax, they give off energy, and the instrument, the H-NMR, picks that up and then graphs it. So, and then the H-NMR will change the frequency of that its magnetic field, and different hydrogens around your molecule will respond to that field differently, which changes um, where those hydrogens wind up on your graph. And you can determine where those hydrogens are, and it's all determined through electron shielding. When you think of these hydrogens, you have to think of how the electrons are interacting with it, which changes how those hydrogens interact with the H-NMR's magnetic field. So if you look at like fluorine and chlorine, fluorine has more electron shielding on hydrogen, or I'm sorry, fluorine has more electronegativity, which lessens the electron shielding on hydrogen, which means that that hydrogen will feel the the magnetic field generated by the instrument, so it will change where it shows up versus chlorine. And um, when if you want to perform an H-NMR in real life, you want to dissolve a little bit of your substance in a deuterium solvent, which is a solvent that has a hydrogen with a neutron, because if the solvent had a proton, then it would show up on your graph because it has a hydrogen that can be resonated. And yeah. Um, you add TMS, which is this molecule here, if you can see it, silicon with 4-methyl groups, and that just calibrates it because all of these hydrogens show up as one peak. Here's an example. It's ethanol. You see here, you can kind of group these by the chemical environments they're in. So if you look at the CH3, you group those together because they're in the same environment. They're all identical to each other. And then the CH2 you group together because they're identical to each other. And then this final hydrogen is grouped with by itself. And you can see these reflected on the graph. You can see the CH2 here, the OH, and the CH3. You can notice that the integral, or the area under the curve, or the height of these peaks, corresponds with how many hydrogens there are. So the OH has 1, the CH2 has 2, and the CH3 has 3. And you can determine where they are on the graph through the chemical shifts, which is going to be found in your IB data booklet. That's you're not going to be able to memorize where things are. You just have to look at the IB data booklet. It deals with that electron shielding. If something is shielded more than something else, then it changes where it is on the graph because it feels the magnetic field differently. And then we'll talk about the rest on the next recording.